Now, let's look at pipes. In the case of pipes, there's some similarities and some differences. In a pipe that is open at both ends, we also can set up a standing wave. We're going to have pressure variations in these standing waves inside the pipe, and the pressure variation is the least at the ends and the most in the middle. And so we get a standing wave pattern that looks something like this. Now, this is a node, this is a node, and this is an antinode. And this would be the mode of vibration that corresponds to the fundamental frequency, F1. So this would be our F1 standing wave. And if you scroll back to our previous page, you notice it has the same number of nodes and antinodes as our fundamental on the string. And that's going to be very nice for us, because that means that the fundamental frequency can be calculated in much the same way. This length of this pipe corresponds to 1/2 a wavelength. And that means that the wavelength of this is 2 times the length of the pipe. And so, solving the wave equation for frequency, we get frequency is v over wavelength, and the fundamental frequency in this case will be the speed of the wave over 2 times the length. In the string, we had to do this elaborate formula to find the speed of the wave. Here we don't. This is the speed of sound, because these are made in air and they propagate through the air as sound waves. If you put the speed of sound in here and divide by 2 times the length of the open-ended pipe, you get the fundamental frequency. The pattern is exactly the same as strings. If we keep this idea that you have to have a node at each end, if we create the next pattern of standing wave, we're going to have something that looks like this. It's going to, if I can draw it worth a darn, look like this. Now the length corresponds to the wavelength, and you can see that is exactly the same as it did on a string. So that's going to create the same pattern for us, which means that F2 is 2 times F1, F3 is 3 times F1, and Fn will be n times F1. So this is in some ways a lot easier, because you don't have to do all that work to find the speed of sound. In most of these problems, you'll be given the speed of sound, or you'll just be asked to solve for it. So that would be a pipe that's open at both ends. However, there's a variation on this that does get a little more complicated. What if we had a pipe that was open on one end, but closed on the other? This would be your typical, if you, I don't know if you've ever done the thing where you blow over the top of a straw while it's down in a liquid, and you hear a certain frequency of vibration. That would be this, or if you blow across the top of a bottle, or if you play an instrument that requires that you put your mouth on one end, like a trumpet or a clarinet. They're closed at one end. Now what that does is it makes it so there's still very little variation in vibration at the open end, but you're going to get more at the closed end. And so you're going to have a node here, but we're going to have an antinode here. Now, the length of this pipe, since it's only from one node to antinode, is only a quarter of the wavelength, which means my wavelength now is 4 times the length of this pipe. What that means is that our first frequency is going to be the speed of sound over 4L. So this pipe would have half the fundamental frequency of a similar pipe that was open at both ends. So our second pattern would be, if we take this, I'm going to draw it a little smaller now, and I'm not going to attempt to get all the waves drawn inside because that's very difficult for me. And if I know that I'm going to have a node at one end and an antinode at the other end, I'm going to have antinode, node, antinode, which means now I have 1, 2, 3 of those intervals, and so the length of this pipe is equal to 3/4 of the wavelength, and the wavelength will then be 4/3 the length of this pipe. Now, if I were to recognize that this is going to be the wavelength that gives me F2, F2 then is going to be equal to the speed of sound over 4/3 the length, which, if I manipulate that a little bit, is going to be 3 times v over 4L. And if you notice, V over 4L is frequency 1, so my second pattern is 3 times my fundamental frequency. But I've seen textbooks that do it one way or the other. Some textbooks will actually call this F2, but I've also seen ones that will actually just call this F3 and just say, hey, F2 doesn't exist. We can't get that. If I do this again, just for the sake of continuing the pattern, we're going to get node, antinode, antinode, node, antinode, node. And now we have 1, 2, 3, 4, 5 of these intervals, which means the length of this pipe is 5/4 the wavelength, which makes the wavelength 4/5 of the length of the pipe, which again, if we plug that in, knowing that this next F, and I'm going to leave the number out, is the speed over 4/5 the length, this will simplify into 5 times V over 4L, and V over 4L again is F1, so F equals 5 times F1, and I'm going to call this F5. And what I think you can see here is that this pattern is going to skip the even-numbered frequencies. So the even-numbered harmonics don't exist on a pipe that is closed at one end. To summarize this, if it is closed at one end, which we call a closed pipe, if it's closed at both ends, well, that's just kind of ridiculous, isn't it? It's not going to make much of a musical instrument if it's closed at both ends. But the fundamental frequency is V over 4L, and the pattern is F1, 3, F1, 5, F1, and so forth and so on. For open at both ends, F1 is V over 2L, and the pattern goes F1, 2, F1, 3, F1, and so forth and so on.